6620 principal component analysis and factor analysis. Let's think a little bit more about this principal component analysis that we talked about earlier. So if we are looking at some points on x, y, and let's just say that these points look something like that. We could think about drawing lines, many different ways. We could think about drawing a line like that. Pretend that's vertical, and we look at the differences between those lines and these points. In which case, we would express that we would look at the perpendicular vector and look at these the variance from those points as well. But I think you'll have to agree with me, knowing, realizing and appreciating the stage that you guys are at right now, that the way that we could express variation the best here would be to look at a line that goes spans the entire x values, looking at these values, making sense that we would come in and also look at the variation from here to here with the orthogonal vector. Now, if we think about this as principal component 1 and principal component 2, we can rotate this between principal component 1 and 2, and essentially we end up getting something, let's just say that looks like this. Now, principal component 1 explains the most variation in our data points, so we might say that we can express more faith, if you will, in principal component 1 and eliminate principal component 2 in explaining the variation between the original data points that we started with back here. So that's exactly what we do with principal component analysis. Is we take the number of variables. So if we have two variables, x and y, then we're going to have our principal component 1 in the orthogonal vector. If we have a situation where we have x, y, and z, then we're going to have principal component 1, principal component 2, and then the third principal component, which would be perpendicular or orthogonal to what we could think of as the base between P1, P2, and P3. And we just go through a process by which we were able to look at each one of these principal components, look at the vector eigenvalues, and ultimately talk about the proportion of variance in the observed variables that is explained by that particular component. So guys, if we, for example, start out with 5 variables, it'd be really cool if you guys could see this, right? We're going to end up think about it, we're going to be living in 5 space, right? So we'll create 5 components. And we're going to have a component 1, component 2, component 3, component 4, and component 5 that will be presented in order in terms of the percentage of variance in the 5 variables that's explained by each component. So let's say, for example, that we find that 82% of the variation in the 5 variables is explained by component 1, and 15% that's explained in variable 2, and 2% and 0.5% and 0.5%. Well, what will happen is these 3 components, component 3, 4, and 5, aren't explaining much of the variation. In fact, nearly all, 97% of the cumulative variation in the 5 variables is explained by component 1 and component 2. So that's why we call it a reduction process. The fact that we're re-expressing the variables as components, which are nothing more than vectors, orthogonal vectors, which is easy to visualize in 2 space and 3 space, but it's kind of weird in 5 space. I can't visualize it. But there may be some of these vectors that really don't go through much of the cluster of data, and we can actually eliminate those. Now, gang, it actually turns out that we do this in simplest form using matrices. So I want to just start out with a real life example here. And let's say that we have, for example, 5 students. All right, and we are interested in, and let me go ahead and tell you, this is going to be a completely, totally hypothetical example. It's completely, totally inappropriate for principal component analysis and factor analysis. But I want to keep it small because I don't want to do a lot of typing in either Excel spreadsheet or in R. So anyway, we're trying to determine factors that are important to students regarding their professor. And let's say that their education is something that students may say is important. Their subject knowledge. I don't know, we may get into a personality, and we may even get into appearance. So we ask 5 students, and obviously we would want to ask more than 5, and obviously we'd want to have more than 4 variables, but we ask 5 students to give scores on the importance, and I'm just going to pull out some scores here that I've written down. 61, 37, 62, 65, and 59, 40, and 45, 43, and 36, 62, 34, 35, 62, 46, and 4340. All right. So student number 5, by the higher score, apparently feels that the professor, high school teacher, whatever it may be, education is most important, and their appearance is least important. While on the other hand, student number 1 seems to think that appearance is important, and education isn't important. I don't know, maybe this person here has a major crush on their teacher or something, so I don't know. But anyway, just hypothetical data that gives us kind of a way to start this. Now, guys, the first thing I'd want to do is I want to enter this data into R, and I'm going to shake things up a little bit because I want to, and I guess because I can. And what I want to do is I want to enter the data in as just as vectors. So I'm going to call the first, I'm going to call this education. And I'm going to enter this in as 32, 61, 59, 36, and 62. And then I want knowledge to be 64, 37, 40, 62, and 46. I want personality to be 65, 62, 45, 34, 43. And I want appearance to be 67, 65, 43, 35, and 40. Now, gang, what I want to do first of all is I want to create a matrix of these values, and so I'm going to call this this matrix just my data matrix. No, I don't want to do that. Let's create a data frame. And the data frame that I want to take a look at here would be E, K, P, and A. And you know what? I'm afraid that I don't have that right, do I? Yeah, I do. Okay, cool. So the data frame here is the 5 students, and we've got the values that I gave in the original data set. Now, what I'd like to do next is I'd like to create a correlation matrix and look at the correlations between the values. And what I can see here is that the correlation between the responses on education and knowledge, there's a negative 0.95 correlation, and you can see that there's very little correlation between education and personality, and a little bit of correlation between education and appearance. Something else that kind of turns out to be highly correlated is the 0.99, which is the correlation between appearance and personality. So, guys, we're going to need this as a matrix. So what I want to do here is I want to save my correlation matrix. I want to save this as just R. Okay, and there's a command in R, the statistical software package, as matrix, and I want to do my correlation of data. So guys, what I now have is I have the same information. It looks to be the same, but now I can treat this as a matrix and perform matrix operations. Now, let me go back over to I guess the whiteboard, however we want to talk about this. Now I want to create a new matrix called the diagonalization of R. And so the diagonalization of a matrix just turns out to give me ones, well, it gives me numbers on the diagonals, and it gives me zeros everywhere else. And it turns out that when we take the diagonalization of the correlation matrix, the process gives us the variance of the correlations. I'm sorry, the variance in the diagonals. So these values right here are going to give us the variance, and it actually turns out those variances turn out to play an extremely important role. Now, the next thing I want to look at is I want to create this diagonalization process by creating a new matrix, and I'm going to call this new matrix L, and I want to diagonalize my matrix R, which is the correlation matrix that we created, and I need to do that by multiplying by 2 new matrices, well, multiplying by the transpose of the new matrix and the other matrix, which I'll call V. Guys, V is what I will call the eigenvector matrix. because the columns, darn it, because the columns of the matrix, the columns of the matrix V give us the eigenvectors, and the values of the main diagonal of L will actually give us the variances, which turn out to be nothing more than the eigenvectors. Now, I don't know how long it's been since you've talked about eigenvalues and eigenvectors. It's something that you can, if you've got an old linear algebra book hanging around, it may not be a bad thing to look at. But guys, in a nutshell, eigenvectors. First of all, they deal with square matrices only, so it's appropriate for where we're heading here with the correlation matrix. And an eigenvector is just a vector. Well, I would say that it's the direction of the vector remains unchanged when a linear combination is applied to it. I don't know. Let's say we have these vectors, and let's just see these things as these vectors as being in a box. And if we could take this end right up here and pull it, in other words, create a linear transformation, you can see that these vectors right here are going to remain unchanged. However, this vector right here is going to be stretched out and have a different direction. It's going to have a different direction and different magnitude. So these vectors right here are called the eigenvectors. Guys, eigenvalues are just nothing more than just the magnitude or the size of the eigenvector. Now, it turns out in R that it's really, really, really easy to find the eigenvectors of a matrix. So if I just use the command eigen of my correlation matrix, what I end up getting is I end up getting these the eigenvalues, and I get the eigenvectors. Now, what I'd like to be able to do now is I'd like to create this new matrix, which I think, what did I call that? The V matrix. So I want to create this new matrix, and I want to use the as matrix again, and I want to use the eigen of R, but I only want the vectors. So now if I look at V, this is going to be the eigenvectors of R. Now, guys, what I want to do now is I want to create my new matrix L. And this is going to be the transpose of V. Guys, remember in matrices we have to do that silly percentage, asterisk percentage to multiply matrices. And we do it of V. So guys, when we get L, what we see here is we get a matrix here where the diagonals actually turn out to be the variances of the components. So the diagonals actually turn out to be the eigenvalues. I'm sorry, they turn out to be the variances. Now, this is kind of clever because this gives us a matrix approach to doing something that is very, very easy to do in in R. So guys, to run a principal component analysis, I'm going to call it my PCA. I can use the command PRINCOMP, and I can run this on my data. I want to run a scores equal true command, and I don't want the covariance, I want to use the correlation matrix, so correlation equal true. Now, if I run my PCA here, and that's not what I want to do, actually I want to run my summary of PCA. Keeping in mind, forget this right here, guys. You're never gonna run this, so eliminate that from your notes. So you're going to run a summary PCA, and again, let's think this through. I have 4 variables, right? Attractiveness, or whatever they were: appearance, knowledge, education, and personality. So what I'm going to end up with here is I'm going to end up with 4 components. And if you look at the components, we have an importance of components table here. And we can see that the standard deviation for the first component is 1.419966. Now, that should look really, really, really familiar if you're really, really, really good at squaring numbers, because that turns out to be exactly what we get on our diagonal of the L matrix. So this L matrix gives us the variance of component 1, which is the eigenvalue, which is just the standard deviation of the component squared. Guys, if we take 1.3933821 and square it, you should know that you're going to get 1.94, which is the value on the second diagonal. Now, all these, it'd be nice if these were showing up zeros and within, certain numeric restrictions on numerical techniques here. That's what we're actually getting on the other components, but or I'm sorry, on the other elements of the L matrix. Now, what's actually happening here is if we look at the proportion of variance, component number 1 is explaining 50.4% of the variance that the 4 observed variables explains. Component number 2 explains 48.5% of the variance. And component number 3, which is, notice we're dropping off each case, with each component, only serves to explain about 1%. Another really important row is this last row, which is the cumulative proportion. So the first component, 50-some%, adding in the percentage of variability that component number 2 is explaining, we can collapse our total principal component analysis from 4 components, from the 4 variables, down to 2 components, and these 2 components again explain almost all of the variance in the 4 observed variables that the 4 components do. So I'm sorry, the 2 components explain 98.9% of the variance that all 4 of the observed variables explain. Now, once we run our PCA, there's some things that we want to run and take a look at. First thing I'd want to look at is just a plot. And if I run a plot of my PCA, I get something kind of cool. What this does is this gives us our variances, and just as we saw here, the variance in the first component is 2.01, so it's slightly above 2, and so on and so forth. To me, and it doesn't work out like this always, but to me, this is clear that we have what's called a 2-component model, because component 3 and component 4 aren't adding much variation or explanation of the variation in our overall model. So just a picture, and there's a way that you can actually draw. If you take a point right here and a point right here, you can connect that line, and there's a way that you can determine where your cutoff should be in terms of your components. But this one's not a very good, well, it's just an inappropriate example, but I wanted to keep it small for obvious reasons. Next thing we may want to do, and this is the one I think really makes things kind of come to a heart, is called a biplot. Now, this is going to give us actually vectors of our components. So component number one, and again, we're living in 4 space here because we have 4 variables. So component A and P, notice that, what was A and P? That would be appearance and persistence. Notice they're pointing in the same direction and approximately the same magnitude, whereas K and E are pointing in opposite directions, but notice that their magnitude is very similar. So that's telling me that my natural loading is that factor 1 or factor 2, whichever it may be, will load on one factor. So A and P, which was appearance and personality, load on one factor, and the other factor would be knowledge and education. That's kind of cool the way that actually turned out. Okay, something else we may want to do is look at what we call our PCA loadings. And our PCA loadings actually give us the correlations between the variable and the component. So we can see that the first variable, which is, I keep forgetting, education, only has a 0.35 correlation with component 1, whereas personality and appearance are highly correlated with component 1. Now when we get into factor analysis, what we're looking at there is we're going to see that personality and appearance are actually creating factor 1, because what we'll do, we'll take 2 components here and we'll ultimately create 2 factors from the number of components. And component number 2, you can see that the other 2 variables were most highly correlated. Now we're not really interested in the negative positive, but we're interested in the absolute value of that. Component 3 primarily drops down because there's very little correlation between component 3 correlation. Okay, that kind of surprises me. We only got a 0.2 correlation here, so all right. This is what happens when you get an extremely small data set. You get kind of wacky things here. Now, let's let me see. What do we want to do here? Let's go back over to the paper. All right, gang. Now let's just so we're clear on. So we've got R is our correlation matrix, and we saw that V has the columns, and we'll just call that the eigenvector matrix. Okay. Now we saw earlier that L was V transpose R V. And it shouldn't take much, many operations to convince yourself that we can solve for the correlation matrix here by taking V times L times the transpose of V. I'm going to leave this connection to you. It's just remember matrices are not commutative, and but you should be able to make that happen pretty easily. So guys, at the end of the day, what we can say here is that the correlation matrix, which is this R, can be expressed as the product of, darn it, the product of the eigenvectors and the corresponding eigenvalues. Now, I want to look at this a different way too. I could take R and re-express this as V times the square root of L times the square root of L. And remember, this L was the eigenvectors. I'm sorry, the eigenvalues. So we can take the square root of those values, which would be just essentially taking the square root of the diagonals. And we can reposition this or reassociate this way. And we can think of this as two new matrices that we can just call A and A transpose. So we can rethink our correlation matrix as the product of A times A transpose. Now, I'd like to demonstrate this for you, and let me see. What I want to do here. All right, gang. This first matrix that we look at here, this A matrix. Let me start a new sheet of paper. Is actually in factor analysis and principal component analysis, this is what we call an unrotated factor loading matrix. And remember, this thing takes a little bit of work, especially in R. The V is not going to be a problem, but the L is. Okay. So what I want to get back over in R to do is, and here's what I want to do. Since we have already run the principal component analysis with 4 components, and what we found here is that C1 and C2 explain, I think, right at 99% of the variation that variable 1, variable 2, variable 3, and variable 4 will say that we have a 2-component model. So what I want my V to be is it's going to be a matrix for component 1, component 2, and of course variable 1, variable 2, down to variable 5. And then I want this matrix to be the square root and zeros here. So the product that I'll get from this will be the unrotated factor loading matrix that we'll use to actually start the rotation process that we looked at earlier graphically. So we need to create this, and you know, I'm probably pretty sure that the way I'm going to do this is not optimal. I have to be honest with you, I really don't know how I'm going to do this just yet. But what I want to do is I want to come back into my V matrix that I have right here, and the only thing I want are just the first two. Is that right? Yeah, I just want the first two columns. So I'm going to create this matrix called V1. And guys, I've forgotten how to do that, to just pull that out. So what I can do here is I can go, so what did I call the eigenvectors? Just V, right? Okay, so I can go V $vectors, and then I can go 1, 2. So I'm going to choose just the first two columns. Let me make sure. Okay, why is that not working? Oh, okay. V1 was V was the vectors. Okay, so I don't need all that. So I just need V1. Okay, this will work. So guys, what you can see is I just came in and pulled out that, right? Yeah. All right, cool. Now, what I'd like to do next is I'd like to bring in, create a new matrix of the square root of the eigenvectors. Or, I'm sorry, the eigenvalues. And that would be the square root of and I'll tell you what I'm going to do. I'm just going to go ahead and create the diagonal of L, and I'll have those numbers there. So what I'd like to do now is I'd like to create L1, which is a matrix of this. And I'd like to have the square root of 2.01 63054 05104. Next I want 0. And next I want 0. And then I want the square root of 1.941513 814. All right. Then I want n numbers of rows to be 2, and columns to be 2, and by row equal true. Okay, exactly. So gang, now if I'll take, I can create my A matrix by taking my V1 times my L1, and this of course gives me my initial factor loading with before I get into any sort of rotation. Well, boys and girls, I think that I am over time, or at least close to time. What I'm going to do next video, I'm going to upload probably more of this. And you know what? I may go through. I take that back. I think what I want to do is illustrate a fuller example, and yeah, I think that's what I'll do. Anyway, I'll make the decision before then, and let you guys know. All right, take care.